Welcome to Hart und Trocken. In this video I want to talk to you about polynomials, about how to factor polynomials, that means how to split them up into smaller polynomials, and how we do this using so-called polynomial division. It's a rather long video, so get yourself a cup of tea, lean back and enjoy the trains of thoughts. In our last video we talked about linear functions. A linear function is of the form y equals ax plus b, where a and b are real numbers, constants, x is the independent variable, and y is the function value of the linear function. The graph of a linear function is a straight line with slope a and y-intercept b. Now we want to talk about another class of functions which we obtain if we take a linear function and add a so-called quadratic term. Those functions are called quadratic functions. A quadratic function has this form where the original linear function is here and the new quadratic term is here. The graph of a quadratic function is called a parabola and typically looks like this. The exact shape and the position of the so-called vertex of the parabola depend on the specific values of a, b and c. In this case, the graph shows the so-called normal parabola, which is the very simple function f of x equals x squared. In a more general case, the vertex typically doesn't sit on the x-axis, and the typical question is to compute the intersections of the graph with the x-axis, the so-called roots. We calculate the roots using the so-called quadratic formula. Let's demonstrate this. The graph we've shown here belongs to the quadratic function f of x equals x squared minus 2x minus 3. Now we look for the two roots. That means we look for the two numbers x1 and x2 on the x-axis such that f of x equals 0. Now the quadratic formula looks like the following. We have x1 and 2 equals minus b plus minus square root of b squared minus 4ac divided by 2a. Well, that is quite a well-known formula, but there are always some people who actually don't know what to use it for. So the answer is to find all x values such that ax squared plus bx plus c equals 0. So we want to have those x values such that this quadratic function takes the value 0. Now let's apply that formula for our example. In our example, we have a equals 1, b equals minus 2, and z equals minus 3. Using these values, we get x12 equals plus 2 plus minus square root of, now b squared, b is minus 2, so we have 4. Now we have 4ac, a is 1, c is minus 3, so that is minus 3 times 4 is minus 12. Now minus minus 12 is plus 12, so we have plus 12 here, divided by 2 times 1, which is 2, equals 2 plus minus. Now, what is under the root? Well, that is 16, so we have the square root of 16 under the root. Let's keep that like this. And now we have 2 plus minus square root of 16, which is 4, divided by 2. And we can reduce that fraction, and we get 1 plus minus 2, divided by, well, 1, which is finally 1 plus 2, which is 3, or, well, 1 minus 2 is minus 1. So we get these two values as the roots for our quadratic function. And if we look at the graph, we see, well, x1 indeed is minus 1 and x2 indeed is plus 3. Now, I told you before that we can think of a quadratic function as starting at a linear function and adding an extra quadratic term. That means a term where x is in the second power. Now we can continue this principle to build the next family of functions, the so-called cubic functions, by starting at a quadratic function and adding a so-called cubic term. A cubic term is a term where x is taken to the third power. So I would receive the following. F of x equals now ax to the third power plus b x to the second power plus c x to the, well, x to the first power actually, plus d, which in fact is something like x to the 0th power. Yeah? Let me just demonstrate you this principle. That's a x to the third power plus b x to the second power plus c x to the first power. Well, actually that is x, but I just want to demonstrate that. Plus d. Now we could write d times x to the 0th power. X to the 0th power is 1. Yeah, but you see the principle now, which of course now can be continued to higher power terms. Now that is something which mathematicians are very good in. As soon as they smell the chance to generalize a principle, well, they do it. So at first they are not happy about these constants or so-called coefficients to be letters from the alphabet, because the alphabet has only 26 letters, and if we generalize that, we don't want to be restricted by the alphabet. So they use the alternative possibility of using an index. That means they rather use a3 to the x times x to the power of 3 plus a2 times x to the power of 2 plus, well, a1 times x to the power of 1 plus a0 times x to the power of 0. So you see a, b, c, and d have been replaced by a3, a2, a1, and a0. So that thing in the blue box now tells us, please, please generalize me. Don't stop at 3. Stop only at, say, n, typical general natural number. So let's do that. Let's instead write an x to the power of n plus a n, and then of course n minus 1, x to the power of n minus 1. And then we have understood the principle. We go one lower each time. So now we are ready to use the dot, 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 the magical dot, dot, dot. And now we show that we have understood the end. Let's say the end is going from 2, a2x to the power of 2, then going down to 1, a1x, yeah, plus, we can still keep that, plus a0. I'll leave away the x to the 0, that's fine then. Now this expression is also a function in x. We throw in some value x, do all these calculations, and finally receive a function value for x. A function of this type is called polynomial of degree n. And we are perfectly ready to switch to the next slide. Now the function in the blue box, p of x, is called a general polynomial, where the orange numbers, an, are constants. They can take on any value from the real numbers. An exception is the term of the highest degree, the first term involving x to the power of n. Here we demand that the constant an must not be 0, such that this term does not vanish. In this case, the general polynomial is said to be of degree n. For the lower power terms, the coefficients are also allowed to be 0, in which case the respective terms will vanish. Here I have printed 3 examples for graphs for general polynomials, which show that they typically look very different depending on the degree and the specific values of the coefficients. However, the graphs of polynomials also have something in common. They are smooth curves which typically cross or touch the x-axis multiple times. One has somehow the impression that they are curved, but they are not curved too much. So it's like a metal piece which is bent. It tries to be not too curvy or not too edgy at certain spots, but somehow tries to equally distribute the curvature or the edginess over its entirety. At the very left and right hand sides, the graph always go either to plus or minus infinity. In fact, a polynomial is very much defined if we know or if we prescribe the roots of the polynomial. That means the intersections with the x-axis. which is why it is a very prominent problem or question to find all roots of a given polynomial of degree n. Finding these roots is equivalent to solving this so-called polynomial equation. So we set the polynomial equal to 0 and try to find all x which solve this equation. There are many methods and techniques of how to do that, and we will talk about some of them now. As I've just said, the equation in the blue box is called the general polynomial equation of degree n, and its solutions are called roots. Regarding polynomial equations of degree n, there's one important fact, namely, the general equation of degree n has at most n solutions. That means a polynomial of degree n cannot have more than n roots. That means that the polynomial which has this graph must be at least of degree 3, because it has 3 roots. Similarly, this polynomial must be at least of degree 3. And this one must even at least be of degree 5, because it has 5 roots. Now, trying to find the roots of a given general polynomial is very closely related to the problem of trying to write the polynomial as a product of other polynomials which have lower degree than the original polynomial. The extreme version of this is to try to write it as a product of polynomials of only very small degree, like 1 or 2. That is also called splitting the polynomial. Ideally, for each polynomial, we would like to be able to split the polynomial only in polynomials of degree 1. Unfortunately, however, that does not work, at least not in the real numbers. But something does work which is almost as good. Namely, every general polynomial of degree n can be written as the product of polynomials of degree 1 or 2. Let's have a look at some simple examples. For instance, we take the very simple polynomial of only second degree, which is x squared plus x minus 12. This polynomial can now be split into 2 polynomials of degree 1. These polynomials are also called linear polynomials, and they have the form x minus 3 times x plus 3. We can easily verify this by simply expanding these 2 expressions, which is x squared, which is x times x, and then we have negative 3 times x, which is minus 3x. And then we have x times 4, which is plus 4x. And finally, we have negative 3 times 4, which is negative 12. If we simplify, we obtain x squared plus 1x minus 12. And check. By the way, from this expression in the blue box, I can directly tell which are the 2 roots of the polynomial, because I take each bracket expression and ask myself, when does it turn 0? The first one turns 0 when I set x equal to 3, because 3 minus 3 is 0. Similarly, this expression turns 0 if I set x equal to negative 4. So the roots of the polynomial are x equals 3 and x equals negative 4. But now let's stay a little abstract for a minute. We want to talk a little about how to factor polynomials. That means how to write polynomials as a product of other polynomials of lower degree. Let's say we have 2 polynomials, we call them p and q, such that the degree of p is strictly greater than the degree of q. In other words, the highest power of x in p is strictly greater than the highest power of x in q. Then we can always find 2 other polynomials, which we call small q and r, so that we can write the polynomial p as, let's call it the orange q of x times the blue q of x plus r of x. Now, before I even give you an example of that with polynomials, I want to show you the very close relation of this idea when using numbers instead of polynomials. Say we have the number 17 and we have the number 5. 17 plays the role of p and 5 plays the role of q. Then I claim that we can always find some other numbers which we don't yet specify, such that, we call them q and r, such that q times 5 plus r equals 17. Here we want q and r to be integer numbers. Well, obviously this equation does have a solution, and it has even multiple solutions. Let's say as an extra condition we want to keep r as small as possible. So respecting this extra condition, the solution is, well, 3 times 5, which is 15, plus 2. That is 17. Actually, what we just did is, albeit in some inconvenient way, to try to divide 17 by 5, hoping to get an integer number as a result. However, as we know, and as it is the case here, that doesn't always work out. The second best we can do is to try to fit 5 as many times into 17 as it is possible. This is 3 times. However, this is only 15, so we have a remainder of 2. Now this is exactly the idea of what we want to do with polynomials. We try to fit q of x as many times as possible into p of x. However, in general, that doesn't always work out. And there will be a remainder, a remaining polynomial of degree which is smaller than q, like the number 2 is smaller than 5, which remains. The method we use, if we are given p and q, and we want to find the orange q and the remainder polynomial, is called polynomial division, a technique I will show you in a minute. For now, let's look at the special case that q of x is a linear polynomial. That means a polynomial of degree 1. That means q of x can be written as x minus some number a. Very simple polynomial. So that general equation is turned into a special version, which is p of x equals small q of x times x minus a plus r of x. We say that the polynomial x minus a is a factor of p of x, well, if the division works out without a remainder. That means if r of x is equal to 0. Let's suppose for a moment that this is the case. That means that r of x is 0 and that x minus a is a factor of p of x. What happens in this case if we plug in the value x equals a into p of x? That means if we calculate p of a. We can evaluate this by plugging in x equals a for all x's on the right-hand side of the equation. Now, if we do that and look at the linear term x minus a, well, x gets replaced by a, which is why we will have a minus a, which is 0. So that part of the right-hand side will turn to 0. And as we have also assumed that r of x is 0, the complete expression gets 0. Consequently, we have found that when x minus a is a factor of p of x, that means if r of x is 0, then p of a is 0. And that means that a is a root of the polynomial p. So what do I want to tell you by that? I want to tell you that whenever we have a polynomial p, and whenever we know that some linear term x minus a is a factor of that polynomial, then we automatically know that this a is a root of the polynomial. Actually, that is not surprising at all. It's just the consequence that we can write it down as a factor. A bit more surprising, however, is the fact that the reverse conclusion is also true. Now admit it's getting a bit confusing, so let's summarize everything in a precise theorem. It says that the two blue-boxed statements are equivalent. The one direction of the argument says the following: If the polynomial Px has the factor x minus a, then we know that Pa equals 0. That means that a is a root of P. That is the direction I've just demonstrated to you. The other direction says that whenever we have a root a of a given polynomial, then we know that x minus a is indeed a factor of this polynomial. So that means that we can sure to be able to split away this factor x minus a from the polynomial. Now that was for sure a lot of theory. If you are not used to these kind of things, I suggest you take a break and re-watch that part of the video later. Anyhow, let's try to justify our hard work by showing you a nice little example. Let's say we have a polynomial p of x, which equals x to the third power minus 3 times x to the second power minus 50. Now the question is here, is x minus 5, the linear term x minus 5, a factor of p? Is x minus 5 a factor of p of x? We could try to figure that out using the method of polynomial division I will show to you in a minute. However, it's much easier to use our new theorem. Because by this theorem, it is equivalent to simply check, is p of 5 equal to 0? And we can easily check that by simply plugging in 5 into p of x. That means we have 5 to the third power minus 3 times 5 to the second power minus 50, which is 125, minus 3 times 25, which is 75, minus 50. And yes, indeed, that is 0. So that's it. We have shown that x minus 5 is a factor. Now suppose that we know an x which solves our new equation. We will now talk about another theorem which also helps finding the roots of a polynomial. It is all about polynomials with integer coefficients. Let's get started with a little motivating example. This is a polynomial of degree 3, which only has integer numbers as coefficients. We check this. Here the coefficient is minus 1, here the coefficient is 4, here it is minus 1, and here it is minus 6. We want to find the roots of this polynomial. Now I'll show you an interesting little trick. If I take the minus 6 to the other side, I get the following. Minus x to the 3 plus 4x squared minus x equals plus 6. Now on the left-hand side of this equation, each summand contains x, which is why we can factor it out. So that gives x times negative x squared plus 4x minus 1 equals 6. That means that we know a root of our polynomial. And suppose further that that x is an integer number. So we suppose that x is an element of z. Then, however, the content of these brackets must also be an integer number. Why is that so? Well, because all numbers in that bracket are integer numbers. All numbers involved are integer numbers. So the content of these brackets is an integer number. Now the consequence of this is that we know something more about x, namely that x must be a factor of 6. The reason for this is that x can be written as x times some integer number equals 6. So consequently, x must be an integer factor of 6. Now what are these integer factors of 6? Well, they're easy to determine. It's 1, it's minus 1, it's 2 and minus 2, and it's 3 as well as minus 3. And of course 6 itself and minus 6 are also possible factors. That is the complete list of all possible roots of the polynomial. So because we have supposed earlier that x is element z, we know that x must be one number from this list. So what is that result good for? Well, suppose you're given some polynomial with integer coefficients and you are asked to find all integer roots of that polynomial. Then you have to simply take the so-called absolute term, which is the 6 here, find all factors, and check these factors for being roots or not. In this example here, if we try all numbers in the list one at a time, we find the following roots: -1, 2, and 3. Now, because our polynomial is of degree 3, we know that these must be all roots. So all roots of our polynomial are integer roots. And using our previous theorem, we can immediately write, which is a complete splitting of our polynomial into 3 linear factors. Now let's summarize these insights in a theorem. Let the coefficients an, an-1, and so on all be integers. Then all possible integer roots of the general polynomial equation must be factors of the constant term. The constant term is a0. Let's have a look at another example. We are supposed to find all integer roots of the polynomial equation in the blue box. Now, can we apply our theorem? No, because the problem is not all coefficients are integer numbers. In particular, there's 1/2 involved. But at a second glance, this is not a problem, because we can multiply the complete equation by 2, which turns all coefficients into integer numbers. So you see that by that little trick, it is very easy to extend our theorem to fractional coefficients. Now we have to take the constant term, which is -2 here, and find all factors. These are +-1 and +-2. Now we test all these 4 possibilities by simply plugging them into the equation. Doing that, we find that x equals 2 is the only integer root. By factoring out the linear factor x minus 2, which belongs to that integer root, using polynomial division, we find indeed that it is the only root. Because that second expression doesn't have any roots in the real numbers. By the way, the reason that I stress the fact that it doesn't have roots in the real numbers is the fact that there is another number system, the so-called complex numbers, in which it does have solutions. But we will not yet talk about complex numbers here. Let's rather return to the idea of factoring polynomials. We start with some polynomial p of x, take some other polynomial q of x, and ask ourselves the questions, well, something like how many times does q of x fit into p of x? Of course, this is only a vague analogy to what we did with numbers, but it's a good way of thinking of it. The polynomial q of x must have smaller degree than p of x. Then we hope to find a polynomial called little q of x, which we can interpret as that q of x fits this many times into p of x. So that is something like the result of the division p of x divided by q of x. And as divisions not always work out, there might remain a so-called remainder, that is the polynomial r of x. If we are lucky, this remainder is 0, that means there is no remainder. In this case, we say that q of x is a factor of p of x. Now, in fact, we have already talked about these things. What is new now is that I want to show you how we can find that polynomial little q of x and how we can find the remainder if there exists one. So now I want to start with a given p of x and a given q of x and find little q of x as well as r of x. The method we're going to use to do that is the so-called polynomial division. Polynomial division is a method which is best explained by simply doing it. So I want to start with a polynomial p of x, which we considered before in our examples. Now remember that we have found integer roots by trying the factors of 6. One of these integer roots was 2. From our earlier considerations, we then know that x minus 2 is a factor of p. In other words, if we try to divide p of x by x minus 2, we hope that this division works out without a remainder. Now this is exactly what I'm going to do now. We choose q of x to be x minus 2, and we want to perform the division p of x divided by q of x. So the first step in the polynomial division is to write p of x on the left-hand side, followed by a division symbol, and then followed by q of x on the right-hand side. Now we perform a procedure which is very similar to the procedure we know from the division of large numbers. We start by looking at the first summand of p, that is minus x to the third power, and looking at the first summand of q, which is x. And then we ask ourselves the question, how many times does x fit into minus x to the third power? In other words, we ask ourselves, by which expression do we have to multiply x in order to obtain minus x to the third power? The answer is minus x to the second power. And this answer is going to be written here as the first summand of the result, minus x to the second power. In the next step, we look at q and multiply q with this first found part of the result. So we multiply these two expressions and rewrite the result of this multiplication below p. So that is x times minus x to the second power is minus x to the third power, and minus 2 times minus x to the second power is plus 2x to the second power, plus 2x to the second power. So what we have written here, this expression, is the result of this multiplication. Now in the next step, we subtract this result of the multiplication by putting a minus sign in front from the expression above, that means from p of x. We do this summand by summand, and we see that the x to the third power terms just cancel away. So minus x to the third power minus x to the third power just cancels away. However, if we calculate 4x to the second power minus 2x to the second power, the result is 2x to the second power. In the next step, we complete this subtraction by writing down these terms next to 2x squared. So minus x minus 6. Now this subtraction has been completed. From now on, the steps we have performed until now are repeated. That means instead of starting with p of x, we now play that game starting with this polynomial. So again, we have to look at the first summand of this polynomial and the first summand of this polynomial and ask ourselves, how many times does x fit into 2x squared? Well, the answer is 2x. And this answer is going to be written next to our first summand of the result, using a plus sign because it's plus 2x. Plus 2x. In the next step, we multiply x minus 2 with this summand 2x. So x minus 2 times 2x, and we take the result and write it underneath this expression. So that is 2x squared, result of the multiplication, 2x squared minus 4x, minus 4x. So that is the result of the multiplication, x minus 2 times 2x. We put this expression into brackets and subtract it from the term above. Again, the summons 2x squared minus 2x squared cancel away. Here, minus x minus minus 4x gives plus 3x. So we have plus 3x. And finally, we have minus 6. So that is the result of the subtraction of these two expressions. And again, we repeat the procedure. That means we look at the first summoned here, and we look at the first summoned here, and ask ourselves, how many times does this summoned fit into this? Well, obviously that is 3 times. So 3 is the result, which we write down here with a plus sign, because it's plus 3. And again, we perform the multiplication 3 times x minus 2 and write down the result down here. So we get as a result 3 times x is 3x, and 3 times negative 2 is negative 6. And again, we put this into brackets and subtract it from the expression above. Now something nicely happens, because you see that perfectly fits, and what remains is 0. The fact that 0 remains down here means that the division has worked out and we are done without having a remainder. The result of our polynomial division is this expression. And we can verify that this is right by simply multiplying minus x squared plus 2x plus 3, which is our result of the division, times x minus 2. And we expect to recover the original polynomial p. So let's do that. X times minus x squared is minus x to the third power. X times plus 2x is plus 2x squared. And x times 3 is plus 3x. Now, negative 2 times negative x squared is plus 2x squared. Negative 2 times plus 2x is minus 4x. And negative 2 times plus 3 is negative 6. We simplify, we get minus x to the third power. Now let's collect all these with x to the second power, which is plus 4x to the second power. And then we have plus 3x minus 4x, which is minus x. And finally we have minus 6. And yes, check. That is perfectly in line with our original polynomial. Let's do another example. Factor the polynomial px, which is given by this, using that it has a root at x equals 3. From our considerations above, we know that x minus 3 must be a linear factor of this polynomial. So that means we expect the polynomial division p of x divided by x minus 3 to work out. So let's perform this now. We rewrite px, which is negative 2 times x to the third power plus 2x squared plus 10x plus 6, and we divide this by x minus 3. And we perform the game of before. We ask ourselves, how many times does x fit into negative 2x to the third power? The answer is negative 2x to the second power. Then we perform the multiplication x minus 3 times negative 2x to the second power, which gives negative 2x to the third power plus 6x to the second power. Put this into brackets and subtract. What remains is 2x to the second power minus 6, which is negative 4x to the second power plus 10x plus 6. And we repeat the procedure, and we ask ourselves, how many times does x fit into negative 4x to the second power? The answer is negative 4x minus 4x. And again we perform the multiplication minus 4x times x minus 3, which gives negative 4x squared plus 12x plus 12x. Put this in brackets and subtract it from the above, which gives, well, negative 2x plus 6. And again we repeat the procedure by asking ourselves how many times does x fit into negative 2x. The answer is minus 2, so we have minus 2 here, and we perform the multiplication of negative 2 times x minus 3, which gives negative 2x, well, plus 6. And again, we are happy because the division worked out. We have 0 here. So the result of the polynomial division is this expression. Let's do one last example. We want to calculate the polynomial division of this polynomial divided by this polynomial. This example is different to the other two examples in two aspects. First, the polynomial by which we divide is not a linear factor, but actually it's a quadratic polynomial. Second, it will turn out that the polynomial division does not work out. That means the remainder will not be 0. So let's see how that works. We start by rewriting the expression x to the 4th power plus 3x to the 2nd power minus 4 divided by x squared plus 2x. The procedure is exactly the same. We ask ourselves, how many times does x squared fit into x to the 4th power? The answer is x to the 2nd power. Then we perform the multiplication x squared times x squared plus 2x, which gives x to the 4th power plus 2x to the 3rd power. Now we have to be careful when we perform this subtraction, because now you see here we have 3x to the 2nd power, but here we have 2x to the 3rd power. So we have to be careful. This term gives, with a negative sign, minus 2x to the 3rd power. And then this term gives 3x to the 2nd power. That means we have plus 3x to the 2nd power. And finally we have minus 4. So that's the result of the subtraction. We can repeat the story. So we ask ourselves, how many times does x to the 2nd power fit into negative 2x to the 3rd power? The answer is negative 2x. Now we multiply negative 2x with x squared plus 2x, and we obtain negative 2x to the 3rd power minus 4x squared, minus 4x squared. If we subtract that, we have 3x to the 2nd power minus minus 4, which is 7x to the 2nd power minus 4. And we repeat the procedure again. We ask ourselves, how many times does x squared fit into 7x squared? The answer is plus 7. So we perform the multiplication, 7 times x squared plus 2x. This gives 7x squared plus 14x. If we subtract this, now things don't work out as we are used to from the previous examples. Because now you see 7x squared does cancel out, but then we have minus 14x and minus 4. Now at this stage we have to stop the procedure. We cannot proceed as we are used to, because if we proceed if we are used to, we have to check how many times does x squared fit into minus 14x. But the degree of minus 14x is 1, whereas the degree of x squared is 2. So that doesn't work out in the way we want to. We rather have to stop here and accept that this expression is the so-called remainder. In terms of our earlier notation, that means that we can write our original polynomial x to the 4th power plus 3x squared minus 4 as the following factorization. That means that is the result of the division, so that is what we have called little q of x. So this is the little q of x, x squared minus 2x plus 7, times the polynomial q by which we divide it, which is this one. This is capital Q of x, so times x squared plus 2x. And finally, plus our remainder. Remainder has negative signs, so we have negative 14x minus 4. So now let's complete our division up here, because what we have written here is not yet complete. And we can do that by adding the remainder, but now in a way that we write 14x plus 4. So note that minus sign, it's a fraction. And in the denominator, we'll have our q of x, so x squared plus 2x. So that here is the correct result of our polynomial division. See, it didn't work out. That means there's still a fractional part which remains. But in some contexts, this calculation is also of use. Okay, that's it for this long video on polynomials. Thanks for watching and see you next time.